Now we are going to start Module 3 of Chapter 1. In this module, we shall discuss the effect of Earth's rotation. Earth's rotation plays a significant role in the hydrodynamics of atmosphere and ocean. In this module, we shall discuss the impact of Earth's rotation, particularly the Ferrel's law, and also the motion of simple pendulum under the Earth's rotation will also be discussed in this module. In this module, we shall discuss Ferrel's law. The equations of motion of a free particle are x double dot minus 2 omega y dot sin lambda equal to 0, y double dot plus 2 omega into x dot sin lambda plus z dot cos lambda equal to 0, z double dot minus 2 omega y dot cos lambda equal to minus g. As the particle is free, so there is no external force. If the particle is projected from the height h, then the initial conditions are x equal to 0, equal to y, equal to z at the origin. The initial velocity are given by x dot equal to u0, y dot equal to v0, z dot equal to w0 at the time of projection. This is the figure. From this you can find that the particle is projected from the point 0, 0, h, that is the point is on the z axis, the height above the horizontal is h, the projection velocity is u0, v0, w0. We consider a particle representing a projectile fired with high velocity in a flat trajectory. This means that u0, v0 are much larger than w0 for nearly horizontal projection. In this case, we have x equal to omega v0 t square sin lambda plus u0 into t, y plus omega u0 t square sin lambda plus omega w0 t square cos lambda minus 1/3 omega g t cube cos lambda equal to v0 into t, z equal to omega v0 t square cos lambda minus g t square by 2 plus w0 t plus h. If u0 and v0 are much greater than w0 and as omega is very small, so we have x equal to omega v0 t square sin lambda plus u0 into t, y equals to v0 into t minus omega u0 t square sin lambda. Therefore, we have x plus iy equal to t into u0 plus I into v0 minus I into omega t square plus u0 plus I v0 into sin lambda equals to u0 plus I v0 into t minus I omega t square sin lambda equals to t into u0 plus I v0 into 1 minus I omega t sin lambda. Let x plus iy equals to capital R into e to the power I phi and u0 plus I v0 equal to capital V into e to the power I alpha. Therefore, capital R into e to the power I phi equals to t into capital V into e to the power I alpha into 1 minus I omega t sine lambda. Now e to the power minus I omega t sine lambda equal to 1 minus I omega t sine lambda plus order of omega square, which is nearly equal to 1 minus I omega t sine lambda. We have neglected the terms containing omega square and higher powers, as omega is very small. Therefore, we have capital R into e to the power I phi equal to t into capital V e to the power I alpha into e to the power minus I omega t sine lambda equal to t into capital V e to the power I into alpha minus omega t sine lambda. This gives capital R equal to t into capital V, phi equal to alpha minus omega t sine lambda. Therefore, the time derivative of capital R gives dr dt equal to capital V, which is constant. Time derivative of phi, that is d phi dt, equal to minus omega sine lambda. That is, the radius vector grows at a constant rate capital V, and at the same time the radius vector turns at a constant rate phi dot is given by minus omega sine lambda. In the northern hemisphere, lambda is positive and the rotation is clockwise when viewed from the above. On the other hand, in the southern hemisphere, it is counterclockwise. This means that the projectile suffers on account of Earth's rotation a slight deviation to the right in the northern hemisphere and to the left in the southern hemisphere. This is the famous Ferrel's law. Now we shall discuss the effect of Earth's rotation on the motion of a simple pendulum, which is known as Foucault's pendulum. Let us consider a simple pendulum of length a suspended from a point O dash, whose coordinate is given by 0, 0, a on the local vertical OZ, such that when at rest, the bob of the pendulum is at the origin of the coordinate system. This is the figure from which you can find the physical description of the problem. Let omega vector is the Earth's angular velocity of rotation and is given by omega vector equal to minus omega cos lambda I vector plus omega sin lambda k vector. Here lambda is the latitude of the place O. First assumption is the motion of the ball is so small that the square, products and higher powers in coordinates and velocities of the bob can be neglected. The motion in z direction is neglected, that is, the motion of the bob takes place approximately on a horizontal plane passing through O. Square of the angular velocity, that is omega square, is neglected. The equation of motion of the bob of the pendulum of mass m relative to the rotating earth can be written as del 2 r vector del t2 plus 2 omega vector cross del t of r vector is equal to f vector divided by m plus small g vector. Here f vector is the externally applied force. In this case, it is equal to the tension of the string, that is capital T vector. Small g vector is the acceleration due to gravity. That is why we have replaced capital F vector by capital T vector and obtain the next line. Omega is the angular velocity, r vector is the position vector of the bob. To eliminate the tension of the string T vector, which is unknown, let us take the cross product with r vector. Taking cross product, we get r vector cross del 2 r vector del T2 plus 2 r vector cross omega vector cross del T of r vector is equal to r vector cross capital T vector divided by m plus r vector cross g vector. Since r vector and T vector are parallel vectors, so the first term on the right hand side vanishes. Thus, we have r vector cross del 2 r vector del T2 plus 2 r vector cross omega vector cross del T of r vector is equal to r vector cross g vector. Here cross means we are considering the cross product of two vector quantities. The first term of the previous equation, that is r vector cross del 2 r vector del T2 can be written as del T of r vector cross del r vector del T, since after differentiation we get two terms which are del r vector del T cross del r vector del T, which vanishes as both are parallel vectors, plus r vector cross del 2 r vector del T2, which have been written here. Using the property of vector cross product, we can write this term here. Right hand side is written as it is. Here dot means we are considering dot product of two vector quantities. We know that r square equal to a square, where a is constant. So, if we take the partial derivative of r vector with respect to time t, we get r vector dot del r vector del t equal to 0. Using this, in the previous equation, we get del T of r vector cross del r vector del T minus 2 into r vector dot omega vector into del r vector del T equal to r vector cross g vector. Here dot indicates that we are considering scalar product, whereas cross indicates that we are considering the vector products of two vector quantities. Moreover, we have the relation r vector equal to sigma vector minus a minus z into k vector. We get this relation from the figure of the pendulum. We have mentioned that the motion takes place horizontally, so we can neglect the motion in z direction. Neglecting motion in z direction, we can approximate r vector as sigma vector minus a into k vector. Therefore, del del t of r vector is approximately equal to del del t of sigma vector. Thus, r vector cross del del t of r vector can be approximated as replacing r and del del t of r vector, we finally get the approximate value of r vector cross del del t of r vector as minus ak vector cross del del t of sigma vector. Here we have neglected the term sigma vector cross del del t of sigma vector, as we have assumed that product term of small quantities can be neglected. Now, let us approximate the term r vector dot omega vector. Replacing r vector by sigma vector minus a into k vector, we get the approximate value of this dot product as minus a into omega suffix z, where omega suffix z is the dot product of omega with k vector, which is the z component of omega vector and is given by omega into sin lambda. Lambda is the latitude of the place. Here we have neglected the dot product of sigma vector and omega vector. Now, let us calculate the approximate value of the term r vector dot omega vector into del r vector del t, which is approximately equal to minus a omega suffix z into del del t of sigma vector. We have already obtained the approximate value of r vector dot omega vector, which is minus a omega z, and the approximate value of del del t of r vector is del del t of sigma vector. So, we get this result. Now, let us approximate r vector cross g vector. R vector is replaced approximately by sigma vector minus a into k vector. G vector is written as it is. This gives sigma cross g vector minus ak cross g vector. G vector can be written as minus g into k vector. Please note that we are considering z direction vertically upwards, whereas acceleration due to gravity acts downwards. So, we have negative sign here. K cross k vanishes since the cross product of same vectors vanishes. So, we get r vector cross g vector is approximately equal to sigma vector cross g vector. Substituting all these in the equation of motion, we get del del t of minus ak vector cross del del t of sigma vector minus 2 into minus a omega suffix z del del t of sigma vector equal to sigma vector cross g vector. This can be written as minus ak vector cross del 2 sigma vector del t2 plus 2a omega suffix z del del t of sigma vector equal to sigma vector cross g vector. Let us take the cross product with k vector. Taking cross product with k vector, we get the final line. Using the property of vector cross product, we can write the first term in this way. Same property has been used in the right hand side of the equation, and we get the first equation written in this slide. Now, k dot sigma equal to 0, since both are perpendicular vectors. So, we have k vector dot del 2 sigma vector del T2 equal to 0. Substituting this result in the previous equation, we get A into second order partial derivative of sigma vector with respect to time t plus 2a omega suffix z vector cross del del t of sigma vector equal to k vector dot g vector into sigma vector. Right hand side can be written as k vector dot g vector can be written as minus g into k vector into sigma vector, which gives k dot k equal to 1. So, we have minus g into sigma vector. Thus, we have del 2 sigma vector del T2 plus 2 omega vector suffix z cross del del t of sigma vector equal to minus g divided by a into sigma vector. Let us consider the equation of motion of the bob in a new frame of reference, which is rotating with angular velocity minus omega vector z about the z axis. So, the operator del del t changes in this way, where del del t equal to del dash t minus omega vector z cross. Now, the second order partial derivative of sigma with respect to time t can be written in terms of new operator, which is del dash t minus omega vector z cross operated on del dash sigma vector del dash t minus omega vector suffix z cross sigma vector. After some calculation, we get del 2 sigma vector del T2 equal to del dash 2 sigma vector del dash T2 minus 2 omega vector z cross del dash sigma vector del dash t plus omega vector suffix z cross omega vector suffix z cross sigma vector. Neglecting the term containing omega square z, we get the next line. Thus, we have del dash 2 sigma vector del dash T2 minus 2 omega vector z cross del dash sigma vector del dash t plus 2 omega vector suffix z cross del dash sigma vector del dash t minus omega vector suffix z cross sigma vector equal to minus g divided by a into sigma vector. This on simplification becomes del dash 2 sigma vector del dash T2 equal to minus g divided by a into sigma vector, which indicates that the pendulum represents an elliptic harmonic motion. In this module, we have discussed the effect of Earth's rotation. Particularly, the Ferrel's law has been discussed. The effect of Earth's rotation on a simple pendulum has also been discussed. It is also known as Foucault's pendulum. It is found that the Foucault's pendulum move in a elliptic path.